So this is week 6 of Applied Thermodynamics Problem solving session. So previous week we looked at 4-stroke cycle and 2-stroke cycles and how they operate. We saw spark ignition engines and compression ignition engines. So we saw how it works and all. So on that we'll extend in this week to see how cycles which are operating in the 4-stroke. So we'll see how the spark ignition engine cycle works. So it was it's called an auto cycle. Then diesel engine which operates in compressed ignition operation. So you'll see a diesel cycle, and there is a dual cycle which is a combination of two. So we'll see that, and also we'll solve some problems on each of it, and also see about knocking and how it happens. And so moving on. So in an internal combustion engine, basically you have a piston cylinder arrangement where the process is happening. So initially there's an inlet valve which opens. While the piston expands, it goes from top to dead center to bottom dead center. Some air comes in, and then it compresses it, during which the valve closes, and the temperature will increase, and pressure will increase, and then you inject fuel, or if there is a fuel air mixture in a spark ignition, you will ignite a spark. So after this there will be combustion taking place, which will generate heat, and your mixture which is there inside, it will combust and it will convert to different components. It will dissociate and it will form some other component in the process of combustion, and it will its temperature and pressure will increase, or based on the process. If it's a SI process, a spark ignition process, your pressure will increase, or else your pressure will remain same in a compression ignition process. So we'll see that cycle. So after that, that will create a power. So it will the piston will expand. It's called a power stroke, and after generating power, you will again piston will move again, and the exhaust valve will open, and the gas will leave. So in actual cycle, some gas will also be retained inside. So this is an open system. So there is some mass flowing in and some mass flowing out. So that is an actual case. But in assuming it to be an air standard cycle, what we assume is, first, that air is a pure air. We don't have any fuel air mixture. So that's what is there. And second main assumption what we assume is that this is a closed cycle. We convert this assumption of an open system, we simplify it, assuming that it to be a closed system. So we assume that there is no mass coming in and going out, but the mass which is there, it's some amount of air which is there inside, and you're doing some work over it. So that's an assumption we make. The third assumption which we make is that there is no change in composition. So the composition will remain same. So it's just air. There is no fuel there, and there is no combustion in all. In actual case, the combustion is happening, and that's what is providing heat. So a similar assumption what goes in air standard cycle is, you are giving in some amount of heat. You are providing some heat as input. So there is no combustion, but we are substituting that with providing some heat. But now we have provided heat, but we know that a cycle cannot operate with just heat in. There should be some heat out. In actual cycle, how this is happening is, during the exhaust process, the gases at which the exhaust is happening are at higher temperature and higher enthalpy. They have some enthalpy. So this is while the exhaust gas moves out or goes out, it takes some part of energy. So this is synonymous to doing a heat rejection. This is what happens in the actual cycle. So in air standard cycle, we assume that there's some heat being rejected. So these are the assumptions that we make, and we also assume that the properties of the air doesn't change throughout the cycle. So these are the major assumptions which we assume to do an air standard cycle to simplify the cycle for an analysis, because we cannot too much complicate it, so it will be difficult. So this is assumptions to make this a process simpler to study it, and we get an estimate of the values to find out the efficiency of the cycle or how much work you get out of it. So to get an estimate, this estimate will be at a higher value compared to the actual cycle, because we have made the assumptions. And also we assume that this cycle is a reversible process. So then we assume that adiabatic expansion is a reversible isentropic process. So reversible, we assume it to be a reversible ideal cycle. So out of which we have 3 cycles in this. We have Otto, we have diesel, and we have dual cycle. So starting, we will start with Otto cycle. In Otto cycle, what happens is initially we have some the straight line is the inlet. So after that you compress it, you compress the gas. So the gas is compressed from 1 to 2. After compression, the gas has reached state 2. So initially it was a state 1 when the piston is at the bottom dead center. It's at the very lowest point. So it will compress, it will move to the top dead center, so through which it will reach 2. So here the volume is not 0, because you have kept some clearance volume. There should be some clearance volume. So that is the clearance volume which is kept. So V2 is the clearance volume. So V1 minus V2 is the swept volume where the piston moves. So this we know. So from 1 it is moving to 2. After 2 we are doing an heat addition. This is, we are assuming that it's similar to the combustion, the energy which is provided. Here we are assuming that a heat is given to the system. So heat is supplied. So it's this is supplied at constant volume. So at top center, when the piston is reached at top center, you are providing heat, and heat is provided at the constant volume. This so in actual cycle, this will not be a straight line, but it could be a curve. It would be a curve, because based on the combustion and when the valve opens, when the spark is ignited, this will be different. It will not be straight line. So 2 to 3 you are providing in heat. So as it is at constant volume, its pressure and temperature rises, so it will reach state 3. So after state 3, this is your power stroke. So it will expand. So piston is expanding, it will reach state 4 after expanding, and 4 to 1 is your heat rejection. So 2 to 3 is heat addition, 4 to 1 or 5 is heat rejection, and 5 to 6 is, you can assume that gas is going out, or we are in the closed cycle, we can just assume 1 2 3 4. So a similar process is shown in the temperature entropy diagram. You see 1 to 2, the expansion and compression is happening at isentropic process, so constant entropy process, and other 2 are constant volume processes. So this is an air standard Otto cycle. The efficiency of air standard Otto cycle, if you define, will be W by W net. So work done in process 3 4 minus 1 2 is the W net amount of work which is generated, divided by heat supplied, Q 3 minus 3 2 in process 3 2, what is the heat supply. So that will be simply on simplification with respect to clearance volume and the pressures, it will come out to be 1 by RC raised to power K minus 1. And similarly there is a temperature entropy diagram which is shown for an Otto cycle. In a DC cycle, what will happen is, we have, instead of a constant volume process, we have a constant pressure process. So from 1 to 2 we have adiabatic compression, isentropic compression. After isentropic compression, we have constant pressure heat addition. So previously there was a constant volume heat addition, but we in DC cycle we do it at constant pressure. So after constant pressure heat addition, what we do is we expand. So 3 to 4 is a isentropic expansion, and again 4 to 1 is heat rejection. So here if you see, previously in Otto cycle we have two constant volume process and two reversible adiabatic process or isentropic process. Here in diesel cycle we have one constant pressure process in which heat is added, and constant volume process where heat is rejected. So and similarly an efficiency temperature entropic diagram is shown for the diesel cycle. So 1 to 2 and 3 to 4 is the work cycle, and 2 to 3 is the, and 1 to 4 are the heat where it's been added and removed. So efficiency here is same, W net by Q. It will be come out to be 1 minus 1 by RC is the clearance volume by the total V1, and K raised to power K minus 1 is the gamma or value. So I represented it as K, which is Cp by Cv. So and we have beta raised to K minus 1, which is V3 by V2. You can calculate that. So using the parameters we can calculate the efficiency of the diesel cycle. In case of a dual cycle is like it lies between an Otto cycle and diesel cycle, where the heat addition in Otto cycle it happened at constant volume, but in a diesel cycle we do it at constant pressure. So dual cycle, the process is split into two heat addition process. It's happens at part in constant pressure process and constant volume process. So 2 to x is constant volume heat addition, and x to 3 is constant pressure heat addition. So 2 to 3 we are adding in heat. It is happening in two ways. So but the other process of the cycle will remain same. In comparing all three cycles, only the heat addition process is different, the other three will remain same. So similarly a TS diagram and efficiency in terms of pressure ratios and volume and cutoff ratio and the clearance volume is given for efficiency for dual cycle. So now we have three cycles, so we'll make a comparison of the all three. We have Otto, we have diesel and dual cycle. So for the, if we have engine for which we assume the compression ratio is same and there is same heat rejection, so what will be the which cycle will be better, or we'll make a comparison here. So assuming that the inlet is same and the compression ratio is same, so your clearance volume and assuming the same, you are having an engine but you are operating it with different cycles. So in this case what's happening is, from a same inlet condition the pressure for the diesel engine we reach state 2 at the end of compression when we reach the top dead center. After that we do a constant pressure heat addition. So 2 to 3C is the heat addition in case of diesel cycle. After 3C we are doing a expansion. So from 3C to 4 will follow, the work will be done, and 4 to 1 there is heat rejection. So 4 to 1 will remain same, because we are assuming constant heat rejection. And then if we assume next is a dual cycle. So dual cycle, the heat addition happens in two stages, so 2x and x3b. So 2 to x, there's a constant pressure, constant volume heat addition, and then constant pressure heat addition. So again it will follow the same path and it will reach state 4. So a dual cycle will be at slightly higher state, because there is a constant pressure and constant volume heat addition. So next, in case of dual cycle, Otto cycle, from 2 we are doing a constant pressure heat addition. So in this case, after doing a constant pressure heat addition, it will reach state 3a, and then the same for the same expansion 3a to 4 for the same heat rejection it reaches state 4. So the cycle for Otto is 1 2 3a 4, and for or dual will be 1 2 3b 4, and diesel will be 1 2 3c. So in this cycle we can see that area under the curve will give you the work done. So for this the diesel will be is less, and compared to the Otto is having the largest one. So efficiency of Otto will be highest for a given same compression ratio, and the least will be for diesel cycle, and dual will lie in between. The same process is shown in the temperature entropy diagram. Here we have 1 2 3 c 4, which is the diesel cycle, then the constant pressure line through which heat addition is happening for the Otto cycle 2 3 a 4, and to some extent there is heat addition in constant pressure, and then it follows a constant volume in case of diesel cycle, sorry, dual cycle. Suppose we need to have a better estimates, we are limiting the peak pressure which is obtained in a cycle. So in that case what will happen is your maximum pressure which the cycle can reach is fixed. So P max is fixed, and we have the same inlet condition. So from there 1 to 2c will be the diesel cycle. So diesel will compress it, and we'll have reached state P max, and then there is a constant pressure heat addition. So 2c to 3 will be diesel, and then will follow expansion. In case of dual cycle, it will be the volume compressed will be slightly less because there is a constant volume heat addition which has to be done. So constant volume heat addition, when you do there's an increase in pressure. So 1 to 2b, after 2b there is a constant pressure volume heat addition. So pressure increases in that case and reach P max. From there we are doing a constant pressure heat addition, and then it expands. And again in case of Otto cycle, it compresses till 1 2a, and then we do a constant volume heat addition to just state P max 3, and then there is expansion. So if you see similarly the opposite is true compared to the previous one. Here the diesel cycle is more efficient compared to the dual, and dual is more efficient compared to the Otto. So when we assume that compression ratios are same, or you say same engine you are operating in different cycles, in that case Otto will be the most efficient and diesel will be the least efficient. But if you assume that the maximum pressure, you are limiting the maximum pressure, then diesel is the most efficient compared to the Otto cycle and dual. And there is a term called knocking and self-ignition. So self-ignition, we need self-ignition when a diesel cycle is operated. So when we compress it, when the fuel is injected, so the fuel has to combust, so it should have a lower self-ignition temperature. But if that is the case in case of operating with the spark ignition, we need a self-ignition to be higher. So what happens is, if that temperature is lower, the fuel which is being compressed can start combusting before the initiation of spark, and it can cause knocking. So if you see knocking, it will happen in SI engine after it reaches the top dead center, and it will be before in case of a diesel engine. And we to point to remember is we need a self-ignition to be lower in case of compression ignition and higher in case of spark ignition engine. And for that which will define octane number and cetane number. So which defines Cetan number, which defines the ignition delay. So higher Cetan number is good for diesel cycle, and for a spark ignition, the fuel having more octane number uh, is good. So if you have more octane number, your knocking will be less. So moving on, we'll see some problems. So first one is, which one of the following process is irreversible in nature? A. Isothermal process. B. Adiabatic process. C. Throttling process. D. None. So this case, we have first isothermal process. Isothermal can be a reversible process. Adiabatic, if it's a reversible, it's an isentropic process, so it can also be adiabatic can also be reversible, but out of which the most reversible will be the throttling process. So the answer is option C, throttling process. So the next one is, an Otto cycle can assume a better example is if you assume the process happened in any of the process mentioned, and if you are able to retrace it to the previous state, then it's called a reversible. But in throttling process, you cannot do that. So assume assume a gas flowing through a valve. So in this case, there is a pressure reduction. If without putting in work, you cannot compress it again, and you cannot retrace the path in the valve. So you cannot just push the fluid with the low pressure through the valve to make it at higher pressure. So that's not possible. So option C is throttling process is an irreversible in nature. So the next question is, an Otto cycle consists of dash. A. Two isothermal and two isentropic processes. B. Two isentropic and two isochoric processes. C. Two isentropic, one constant pressure and one constant volume processes. And D. Two isobaric and two isentropic processes. So if you see in this, we have been asked for Otto cycle. So if you see, option A is two isothermal and two isentropic process. If you recall, this is Carnot cycle. So we have two isothermal, heat addition and heat rejection, and two isentropic processes where compression expansion happens. And if you see, option B is the Otto cycle, two isentropic and two isochoric process. Isochoric is constant volume. So we have constant volume heat addition and constant volume heat rejection, and two isentropic is for the compression and expansion process. And if you see, option C is the dual cycle. We have two isentropic and one pressure and constant volume. It's a dual cycle. Diesel cycle, because constant volume heat rejection and constant pressure heat addition. If the heat addition is also split into two, then it's a dual cycle. C is a diesel cycle, and D is two isobaric and two isentropic will be Brayton cycle, which we'll be seeing in the coming weeks. So the answer is option B. So moving on, we have, for same maximum pressure and temperature, the air standard thermal efficiency for a diesel cycle is higher than Otto cycle. So here we are saying that we have maximum pressure and temperature is same for all the cycle. So which of the air standard thermal cycle will be higher, diesel or Otto cycle? So we just discussed. So if you have constant compression or clearance ratio, same cycle, compression ratio, so in that case, constant compression ratio and heat rejection, we'll have Otto, which is more efficient and compared to diesel. But if we limit the maximum pressure, so the maximum pressure is same, so in that case we'll have diesel cycle, which will be more efficient than the Otto cycle. So in this case, option A is true. So we'll move on. We'll see the Otto cycle, designated OC, and diesel cycle, designated as DC, have the same compression ratio and they undergo same amount of heat rejection. Which of the following statement is correct for air standard efficiency? So okay, it's the same thing which we saw here. The compression ratio is same and same heat rejection. So OC is more efficient than DC, DC is more efficient than OC, both are equally efficient, then the air standard efficiency cannot be predicted. So in this case, we know that for constant compression ratio and same heat amount of heat rejection, Otto cycle will be more efficient than the diesel cycle. So answer is option A. Next we have, in dual cycle heat addition takes place at dash. So in dual cycle heat addition, so we know we compared 3 cycles, so it will have, options are at constant volume, first at constant volume, then at constant pressure, then constant pressure, none of them mentioned. So we know in dual cycle we will be taking in 2 stages, at constant volume and then at constant pressure. So it will be in two stages. So answer is option B. First it will be at constant volume and then it will be at constant pressure. So moving on, we have the actual volume of charge admitted in a 4-stroke engine is dash. So options are equal to the stroke volume, equal to stroke volume plus clearance volume, C less than stroke volume, D more than stroke volume. So I'll see, answer will be less than stroke volume. If you think, if you in actual cycle you have after exhaust, it will not, the gas will not be totally pushed out. It will be, there will be some gases which will be present in this piston cylinder, and then when it expands, and that will it will take some volume. So that exhaust gas which is present, it will be at a higher pressure. So when the inlet valve opens, the piston would have already been lower than the top dead center. So it will be, volume will be more than clearance volume. So if it's more than clearance volume, the actual volume of the cylinder, maximum volume, it will be clearance volume plus the swept volume. So initially the exhaust gas will expand and it will come to an suction pressure, and so inlet valve when it opens, some gas can come in. So it will take some more volume greater than the clearance volume. So what happens is, now the volume which the inlet gas can occupy has come down. It has come down from stroke volume. So it will be less than stroke volume. So the answer is option C. So next question is, if the compression ratio of an Otto cycle is increased from 5 to 7, then the percentage increase in the air standard efficiency will be. So we know Otto cycle, so we are saying the Otto cycle, instead of compression ratio being 5, we are increasing it to 7. So how much will be there be a change in efficiency of an air standard efficiency? So efficiency is defined as we already saw, as 1 minus 1 by compression ratio raised to power k minus 1. So for air we are assuming it to be 1.4 or 1.35. So on substituting 7 by 5 for, because compression ratio 1 by RC. So on taking a ratio of the efficiencies, we will get RC of state 2 by RC of state 1. 7 by 5 raised to power 0.4. It's 1 point, so there will be increase in 14%. So answer is option D. So the next question is, the self ignition or pre-ignition or auto ignition, all terms are same, is desirable for SI engine. Is the self ignition desirable? So spark ignition you are providing a spark to ignite it. So there is no requirement for self ignition. Self ignition is required in case of a compression ignition engine. When you compress it, the temperature increases, and that temperature is sufficient to self ignite the fuel. So that there self ignition is more desirable. Here self ignition will call knocking, so it's not desirable. So in case of an SI engine, it's false. The next question is, the working cycle of an 4-stroke engine is said to completed at dash number of revolution. So at what number of revolution is the 4-stroke engine cycle gets completed? So 4-stroke means there is a movement of piston 4 times. It will move from top dead center to bottom dead to top dead. So that swept volume, how it's moving, there is four movement. So each revolution there will be 2 movements. So in this case, so 4-stroke will take 2 revolution. So in 2 number of revolution it will complete a 4-stroke. So moving on, we have in air standard cycles, it is assumed that the real open cycle is changed to closed cycle by assuming that combustion products exhausted to atmosphere are fed back with fresh charge in the intake system. So in air standard cycle, it is assumed that the real open cycle is changed to closed cycle. So that is true, and the combustion product exhausted to atmosphere are fed back with fresh charge. So this statement is true. So this is the assumption which we made, and to simplify our real cycle. So statement is true. So moving on, we will see some numericals on each of the cycles. So first is we have cylinder conditions at the start of compression in an spark ignition engine operating on an air standard Otto cycle. So we are considering a spark ignition engine, so which is operating on Otto cycle. So cylinder at initial start of the compression, so state 1 we are assuming here, which is given as temperature 60 degrees Celsius and the pressure is 98 kilopascal. So we'll first we'll name the Otto cycle. So we know state 1 where it's starting, to inlet cycle where it starts. So we are assuming that air is there inside, so that is at 60 degrees and 98 kilopascal. So we know state 1. So the next is the engine has a compression ratio of 9.5:1. So we know the compression ratio, okay, and uses gasoline with air fuel ratio as 15.5. So we also know air fuel ratio, and compression ratio is given. So it says that combustion efficiency is 96%. So combustion efficiency is also given, and it can be assumed that there is no exhaust residual. So there is no exhaust residual, okay. So what all has to be calculated? So temperature at all states in the cycle, so brackets units which it's wanted, so degree Celsius. The pressure at all states in the cycle, specific work done during power stroke, and pressure and temperature at all points, and specific work during power stroke. So 3 to 4 we need work done, specific work done. Then heat added during combustion, 2 to 3, this is a combustion process. So net specific work done, so total work, and then indicated thermal efficiency. So from the cycle we'll get only the indicated power, because we don't know the frictional power. So actual, that's why this is called an indicator diagram in the PV. So we get an indicated efficiency. I can calculate from the power, total power which we get, so which will be equal to indicated power. So the process for the spark ignition engine Otto cycle is shown here. So if you see 1 to 2 is adiabatic, reversible adiabatic compression is happening from 60 degree and 90 to 98 kilopascal. So we know the state point. From there is compression, then heat addition because of combustion, 2 to 3, then 3 to 4 is work being done, the work is produced. So 3 to 4 expansion, and 4 to 1 is heat rejection again. So now we need to find out initially the state points at each of the other states, 2, 3 and 4. We need to find out the pressure and temperature. So we'll start. We know at the start we know the temperature is 60 degrees Celsius. So converting that into Kelvin plus 273, we need 333 Kelvin, and pressure is at state 1 is 98 kilopascal. So now we know the compression ratio 9.5. So we know V2 by V1 by V2. So V1 by V2 is known. So if we know that, then this is a constant PV raised to power gamma, reversible adiabatic. So PV raised to power K we assume. So in that case we'll know that T2 equals T1 raised to power RC, compression ratio V2 by V1, V1 by V2 raised to power K minus 1. So on substituting, RC is 9.5 compression ratio, and we know temperature at the start 333, and then K is we are assuming 1.35 for air, so 0.35. On substituting that, we will get 732 Kelvin, so which will be equal to 459 degrees Celsius. So now T2 is known. Either we can use T2 or we can use the compression ratio directly. So pressure can be calculated. We know pressure 1. So pressure at state 2 is P2 equals P1 into RC raised to power K, the compression ratio. So this is a simple adiabatic process. So from there, so compression ratio is known, K is known, we substituting 98 into 9.5 into raised to power 1.35. So we'll get 2047 kilopascal. So now this is known, and we are assuming that the calorific value of fuel is 43,000. I'll mention it here. So calorific value of fuel is 43,000, and we also know the combustion efficiency, which is 96%. So we can find out how much heat is being given into the cycle during process 2-3. So during process 2-3, the heat given provided is mass of fuel into calorific value. So there are total values 43,000 into 0.96. So here heat is added because see the cycle heat which is provided Q in because of combustion, Q into thermal efficiency into mass of fuel will be equals to in the cycle we have combination of fuel and air. So m dot F plus m dot A into, this is happening at constant volume, so CV into T3 minus T2. So that is the process 2 where is heat is added. So heat added is m dot F into the calorific value of fuel into combustion efficiency. So that is the amount of Q which will be added, which will be equals to m dot F, fuel plus air combination total mass, into constant volume, so CV into delta T. So we know that. So m dot F we are taking it down, so here to the right hand side. So we'll get m dot F by m dot F will be 1. So m dot A by m dot F is air fuel ratio. So we have simplified that, and air fuel ratio is given in the problem as 15.5. So we substitute 15.5 plus 1, and CV is 0.821 into, we know temperature at state 2 we have already calculated. So on substituting that, and we know calorific value 43,000, and combustion efficiency is also known. So using that we can calculate the temperature at state 3. So that will come out to be 3779 Kelvin, and can convert that into degree Celsius, we'll get 3506. So now the remaining process is state 4. using 3 4 which is a reversible adiabatic process. So similar to how we calculate in state 2, we can calculate state 4. So T4 equals T3 by 1 by RC K minus 1, because the volume at state 3 and state 4 is similar to state 1 and state 2. So we can straight away use the compression efficiency, and we can calculate temperature 4. So T3 we have already calculated. Similarly, pressure at P3. P3 here, this is a constant volume process. So PV, assuming it's an ideal gas, PV equals to MRT. So volume is constant, so P by T will be constant. So P3 by T3 equals to P2 by T2. So from there we can calculate P3. We have already calculated P2, so which is 2047, and we know the temperatures. So it will come out to be 10,568 Pascal. Kilopascal. 10,568 kilopascal. And T4 is similarly the reversible adiabatic. We can calculate. It will come out to be 1719 Kelvin and 1446 degrees Celsius. And P4 will come out to be 506 kilopascal. So now we have calculated all the temperature and pressure at each of the state points. Next is we have been asked to calculate the specific work done during power stroke. And during power stroke is the process 3 to 4. So specific work done will be, this is being an adiabatic process. So we know the work done in adiabatic process is mr delta T by 1 minus gamma, or gamma minus 1, the way temperatures are written. So here specific work, so divide by mass, so we'll get R T4 minus T3, or if you know pressures and volume, we can also use that P1 V1 minus P2 V2. We can use that by gamma minus 1. Here we don't know volume, we just know compression ratio. We can calculate volume at state 2, but we know the temperatures and the K value, so we'll directly use the formula given here. So R T4 minus T3 by 1 minus K. So T4 and T3 is known and K is 1.35. So substituting that, we'll get 1689 kilojoule per kg. So this is a specific amount of work which is being produced in the power stroke. So the next question was to calculate heat added during combustion. So heat added during combustion, you can easily calculate. So this is specific heat added during combustion. So CV T3 minus T2. So we'll get 0.821 into 3779 minus temperature T2 is also known 732. We'll get 2502 kilojoule per kg. So specific heat added is 2502 and specific work in the power stroke is 1689. So for net specific work done, we need to calculate the work done in process 1 2 while compressing it. So similarly how we calculated in power stroke, the same approach. So R T2 minus T1 by 1 minus K. We know we have already calculated temperatures. We are substituting there. 732 minus 333 divided by 1 minus 1.35. So in this case we get as minus 327 kilojoule per kg. Minus negative because it's been done on the system. So minus 327 kilojoule per kg. So total net work done is, so what is done in power stroke plus what is done in the compression process. So W12 plus W34 is minus 327 plus 1689. So net work is 1362 kilojoule per kg. So the next question is to find out the indicated thermal efficiency. So indicated thermal efficiency, we have already calculated the network, specific network, and also specific heat added is also known. So we can straight away take a ratio of it, we will get indicated thermal efficiency. So W net by Q is 1362 by 2502. So it will give us 54.5%. So that is the indicated thermal efficiency, or we can use the formula for Otto cycle, or 1 minus T1 by T2, because uh, in terms of compression ratio, if we write in terms of uh, compression ratio is between state 1 and 2, so we can use the temperature as well instead of volumes. So in terms of temperature, it will be 1 minus T1 by T2. In terms of compression ratio, it will be 1 minus 1 by RCH per K minus 1. If we use the same relation, we will get the same value of 54.5% as the indicated thermal efficiency. So we have calculated all which has been asked for. So we'll move on, we'll see how to solve a diesel cycle. We have a compression ignition engine which is operating on the air standard diesel cycle, which has a cylinder condition at the start of compression as 65 degrees Celsius and 130 kilopascal. So state 1 is known. So 1, 2, 3, 4 is the process, diesel cycle process. 1 to 2 reversible adiabatic, 2 to 3 constant pressure heat addition, 3 to 4 is the power stroke work which is produced, and 4 to 1 is the heat rejection. So in the question, in the compression ignition, we know the start point which is given as 65 degrees Celsius and 130 kilopascal, and they are saying the light diesel fuel is used at an equivalence ratio of greater than 0.8, greater than or equal to 0.8. So we'll assume equal to 0.8 with a combustion efficiency of 0.98. So combustion efficiency is also given, and specific calorific value we assume at 43,000. So compression ratio is also given as it's RC is 19, and stoichiometric air fuel ratio is 14.5. So m dot A by m dot F is 14.5. So in this case too, we are asked to find out temperature and pressure at all the state points. So 1 is already given, so we need to find it at 2, 3 and 4, and pressure at each state of the cycle. Okay, cutoff ratio, and then indicated thermal efficiency and heat lost in exhaust. Okay, we'll see how to solve this. So state 1 we know 65 degrees Celsius, it's in 338 Kelvin converted unit, and then pressure is 130 kilopascal. State 2 we know that this process is reversible adiabatic, so PV raised to power K or gamma which will be constant for the reversible adiabatic process. So in terms of temperature and volume, the relation is T2 equals T1. RC is V2 by V1 raised to power K minus 1. Sorry, V1 by V2 raised to power K minus 1. So using this, we substitute the compression ratio, and we know temperature at the state point 1. So we can find out temperature at 2. It will come out to be 947 Kelvin. And K value we are assuming 1.35 for air. And P2 similarly we can find out PV raised to power K. So similarly P2 equals to P1 into V1 by V2 raised to power K. So on substituting all the values, we will get pressure at state point 2 as 6922 kilopascal. So here the catch here is they have given equivalence ratio and stoichiometric fuel air ratio. So this cycle is not operating at stoichiometric fuel air ratio, but this is phi is greater than or equal to 0.8. So if we assume 0.8, this is a lean mixture. So now actual air fuel ratio is stoichiometric fuel ratio divided by 5. So it will be 14.5. So divided by 0.8, it will be 18.125. So if you see m dot A by m dot F, so m dot A value is 18 times. So stoichiometric value is 14.5. So this is a lean mixture. So we have calculated the actual air fuel ratio, and then the next is we'll find out the temperature at state 3. So here the calorific value is 42,500, and combustion efficiency is given as 98%, so 0.98, and in terms of written in terms of air fuel ratio instead of mass. So in here it will be m dot F into Q into combustion efficiency equals to m dot F plus m dot A for the process in the cylinder. So m dot f, if you divide it on both sides, so you'll get a air fuel ratio plus 1. So that is for process 2 3. So T3 minus T2, which is happening at sorry, this should be constant pressure Cp, not Cv, Cp, because this is happening at diesel cycle, which happens at constant pressure. So AF plus 1 Cp T3 minus T2. So I substituted the calorific value 42,500 into 0.98. Air fuel ratio we have calculated 18.125 plus 1 into Cp value is 1.108, and we have calculated T2. Substituting, we can calculate state at temperature at state 3. So will come out to be 2640 degrees Celsius, and we know the pressure is constant, so P2 pressure is equals to P3 pressure, so 6922 kilopascal. And also we need to find out the volumes. So V4 equals to V1, so we can find out from ideal gas relation PV equals to RT. So RT1 by P1, we are taking specific volume here, so 0.287 into 338, we already know state 1, and pressure is also known, so that will come out to be 0.7462 meter cube per kg. And V3 is same, RT3 by P3. So similarly, we have already calculated temperatures and pressure at state 3, so it will come out to be 0.1208 meter cube per kg. So now remaining is to calculate temperature and pressure at state 4. Similar to what we did in process 1 2, this is also a reversible adiabatic process. So we can we have already calculated the compression ratio for process 3 and 4. So using that, V3 by V4 raised to power k minus 1, we have already calculated V3 and V4. So substituting that, we will get temperature as 1267 degrees Celsius, and pressure at 4 will come out to be 592 kilopascal. So now we have already calculated each of the states pressure and temperature. So question A and B is done. Now we have been asked to calculate cutoff ratio, indicated thermal efficiency, and heat loss in exhaust. So cutoff ratio is nothing but T3 by T2 or V3 by V2. This is V3 by V2 cutoff ratio. So here this being a constant pressure process, we can write it in terms of temperature also, or we have to calculate V2 and then substitute. So we know temperature, we are substituting that T3 by T2 will come out to be 2913 by 947, which is 3.08. Then we've been asked to calculate indicated thermal efficiency. So we know the diesel cycle efficiency formula, so which is 1 minus 1 by RC raised to power k minus 1 into bracket beta. Beta is the cutoff ratio which we calculated, raised to power k minus 1 divided by k into beta minus 1. So we know we have already calculated compression ratio, we know k value, we know beta value. So substituting all that, so we can find out the indicated thermal efficiency, which will come out to be 54.7%. So the next question is to calculate the heat lost in exhaust. So heat lost is again in the cycle, it's happening at constant volume. So Q into will be CV T3 minus T2. So you have to substitute that. So and we already know the temperatures, so substituting that we'll get 2178 kilojoule per kg. Then W net will be Q times of thermal efficiency. So thermal efficiency we have already calculated for 54.7%, so it will come out to be 1191 kilojoule per kg. So sorry, Q, this is Q in, Q is Q in, so which is happening at constant pressure Cp. So Q is Cp T3 minus T2, so it will come out to be 2178 kilojoule per kg. Then we know Q in, we know thermal efficiency, we can calculate the work done. So thermal efficiency is calculated 0.547, so it will be 217 into 0.47 will give you the W net. and being a cycle operating cycle, the W net will be equal to Q net. So W net we have already calculated. Q net will be just Q coming in and Q the exhaust. So the difference of the Q in and the work done will give us the exhaust heat which is going out. So 2178 minus 100,191 1 will give a 987 kilojoule per kg. This is the amount of heat which is lost, or the exhaust gas which is taken. So we have found out all which has been asked in the question for a diesel cycle. So now we'll move on. We'll see for a dual cycle. So a compression ignition engine for a small truck is to operate on a air standard dual cycle with a compression ratio of RC of 18. So compression ratio is given for 18, and the engine is working on a air standard dual cycle. Due to structural limitation, maximum allowable pressure in the cycle will be 9000 kilopascal. So initial case we are saying we are limiting it to 9000 kilopascal. So, and light diesel fuel is used at air fuel air ratio of 0.054. By saying the combustion efficiency can be considered as 100%. Okay, and cylinder condition at the start of compression are 50 degrees Celsius and 98 kilopascal. So initial condition is known, and we are limiting that pressure, maximum pressure which we can reach, to 9000 kilopascal, and fuel air ratio is given, compression ratio is given. So next is we have been asked to calculate, saying that maximum indicated thermal efficiency possible with this condition. So what can be the maximum indicated thermal efficiency which is possible, and second, peak cycle temperature under conditions of part A, peak cycle temperature, and then similarly minimum indicated thermal efficiency possible, and similarly we need to find out the peak cycle temperature in this case. So state 1, we have state 1 which is already given as 50 degrees Celsius and 98 kilopascal. So state 1 is known, and from 1 we are compression ratios known, so we can find out state 2. So state 2 is known. Now the process in which the heat is added determines how whether the efficiency will be maximum or minimum. So in this case we need maximum allowable pressure is limited, and it says maximum indicated thermal efficiency. So maximum is possible when this pressure most of the heat is added at state 2 in constant pressure process, constant volume process. So if, because this thermal efficiency are we are operating in 2 cycles, so it will be maximum when for the given compression ratio if the heat is added mostly on the constant volume, so it will reach the higher peak value at that point, and then we continue adding the remaining amount of heat. So maximum work is possible when it is close to Otto cycle. So from 1 to 2 we have reached for both the cycles, assuming irrespective of the thermal efficiency, assuming we have reached 2 because 2 will be less than the peak value, assuming x is the peak value, peak pressure which can be possible. So if maximum work can be taken from this when constant pressure constant volume heat addition is done, and then constant volume is done smaller amount, a larger amount of heat addition is done in a constant volume process. So this will become close to the Otto cycle. So this will have the maximum thermal efficiency, and if it is operated at from 2, we instead of we don't go to peak pressure, but we do it a constant volume constant pressure heat addition operating at a diesel cycle. In that case, we'll have a minimum thermal efficiency. So we can only know at state 2 how the process will be. So state 2, we know state 1, state from 1 to 2 is a constant reversible adiabatic process. So compression ratio is known, so we can calculate temperature at state 2 and temperature and pressure at state 2. So at state 2 temperature is 615 degrees Celsius and pressure is 4851 kilopascal. But we know that maximum pressure limited is 9000 kilopascal. So we have a large difference, so close to 4150 kilopascal pressure difference is there. So we can utilize that. So we can increase the pressure by doing a constant volume heat addition. So at state 2, the temperature at state 2 will be, this being a constant volume process, we can find out P by T as constant. So using that we can find out temperature at state 2, which will come out to be 1647. Peak pressure is known, 9000, so Px is 9000 and P2 is 4851, and X and 3 will be same, pressure will be same, peak pressure. So at Tx the temperature is 1647 Kelvin. Now air fuel ratio is nothing but m dot reciprocal of fuel air ratio. So we can find out air fuel ratio is 18.52, and the Q supplied in the process is m dot F into Q calorific value into combustion efficiency, which will be equals to m dot F plus Ma, and constant volume process Cv T2 minus Tx minus T2 plus constant pressure process m dot F plus Ma into Cp T3 minus Tx. And we know that assuming combustion, we are given the combustion efficiency is 100%, so efficiency of combustion will be 1. We differentiate divide both sides by mass of fuel, so we will get in everything in terms of air fuel ratio. So in this case we know the calorific value is 4,500 for diesel, and we substitute air fuel value, we know Cv, Cp, we know Tx, T2, we already calculated. We can find out the temperature at state 3. So temperature at state 3 will become 3050 Kelvin. So using that we can find out the pressure ratio, which is Px by P2, and then the cutoff ratio for constant volume, P3 by Px, T3 by Tx for constant pressure, and thermal efficiency, the dual cycle is defined as 1 minus 1 by compression ratio raised to power k minus 1 plus alpha into beta raised to power k minus 1, cutoff ratio and pressure ratio, and divide by k alpha beta minus 1 plus alpha minus 1. So that's the dual cycle formula. Either way, if you can also calculate from the state points which is already there, you can find out the work done and the Q supplied also we can be found out, and specific Q supplied and specific work done, and you can find out the efficiency using that as well. So we know the dual cycle formula, so we can straight away calculate. So thermal efficiency is known, so 60 point, it will come out on substitution of all the values, we will get a 60.3%. So the maximum efficiency if the cycle operates as a dual cycle will be 60.3%. So and the peak temperature is T3 3050 Kelvin, so it will be 2777 degrees Celsius. So that is the peak temperature which you can obtain. Then the minimum thermal efficiency, so minimum thermal efficiency, as I told, for a given compression ratio, Otto cycle will have the maximum thermal efficiency, then comes dual cycle. So we operated, because of the pressure was limited, we operated it as a dual cycle. Then the minimum efficiency for a given compression ratio in Q rejected will be for diesel cycle. So minimum thermal efficiency can only be we can obtain when whole of the heat addition is given at constant pressure. So after reaching state 2, instead of adding heat at constant volume, we do it at constant pressure, operated as is a diesel cycle. So from then we operate as 1, 2, 3, C, 4. So if we operate a diesel cycle, we'll get same, we do heat addition as constant pressure. So air fuel ratio plus 1 into Cp T3 minus T2. We know calorific value 42500. So we substitute air fuel ratio and we substitute temperature at state 2, which we have calculated previously. On substituting that and Cp value 1.108 for air, and we get state 3 temperature as 2853 Kelvin, and cutoff ratio as beta T3 minus T3 by T2. Similarly, what we calculated previously. Similar here, this being a diesel cycle, so thermal efficiency of diesel cycle is given, or if you substitute alpha as 1, the dual cycle will get converted into thermal efficiency. For dual cycle, thermal efficiency dual cycle will convert to diesel cycle thermal efficiency. So on substituting, we have already calculated cutoff ratio. Then substituting that, we'll get efficiency as 53.3%. So this is 53.3%, and this is the minimum efficiency which you can get out of the given initial temperature conditions here. But we are not utilizing the maximum pressure which you can get. So but if we operate this condition, reduce the compression ratio, increase the compression ratio to reach this higher pressure, so this cycle will be more efficient. Operating this as a diesel cycle will be more efficient compared to what we got, 60.3, so it will be more than 60.3. Because this is the same engine, the compression ratio is limited, we are getting here thermal efficiency is 53.3%. At this condition, the temperature is 2580 degrees Celsius. So if you see here, the pressure at which heat is being added is 4851. So here 4851. If you goes still higher pressure, so that you can utilize a much more of the cycle, and you can get a better efficiency. For this given condition, this is providing 53.3, which is lower than dual cycle because of the limitation of the compression ratio. Okay, and peak temperature is calculated is 2580 degrees Celsius. So moving on, we have a C4H8. So it could be a butane or isobutane. Is burned in an engine with a fuel-rich air-fuel ratio. So there's a rich in fuel is rich, and dry analysis of the exhaust gives the following volume percent. So they are doing a dry analysis, so water is not considered. So CO2 is saying it's 14.95%. Isobutane, butane or isobutane is 0.75%. CO is 0%, H2 is 0%, O2 is 0%, with rest being nitrogen, N2. Higher heating value of the fuel is 46.9 megajoule per kg. So write the balanced chemical equation for 1 mole of this fuel at this condition, and calculate air fuel ratio, equivalence ratio, lower heating value of fuel, energy released when 1 kg of the fuel is burned in the engine with a combustion efficiency of 98%. Okay, so we don't know what amount of fuel is being used to burn it. So X amount of, we are considering X amount of C4H8 is being used, then y amount of air is being taken. So air, we are assuming that it contains of oxygen and nitrogen is 3.76% because 21% and nitrogen is so we are converting that to mass space. So y moles of oxygen and y moles of nitrogen is there, 3.76 times of oxygen, so 3.76 y of nitrogen. So this is getting combusted and we are getting that 14.95% of CO2 plus 0.75% of uh, fuel which is burning is present, plus 84.3% of nitrogen is there, and some amount of water will also be there because this being a dry analysis, we are water is not given. So now each component balance conservation if you do, so initially we are doing a nitrogen conservation, so for to find out y, so we know 14.595 plus 0.75 minus 100 will be the percentage of nitrogen which is present. So we can find out that, so 84.3 and so y times 3.76 will be equal to 84.3. From there we can find out how many moles of air is being used, so it will come out to be 22.42. So next we are doing a conservation of oxygen. So now we have calculated y, so 2 into 22.42, this will be equals to 14.95 into 2 plus there is a water, so z plus z. So doing simplifying it, we will get the amount of moles of water present is 14.94. So we have calculated z. Now remaining is the amount of fuel which is being initially used. So either we can do a carbon balance or you can do a hydrogen balance. So we are doing here a hydrogen balance. So 8x will be equals to 2 into 14.95, sorry 14.95, sorry this is a hydrogen balance. So 8x equals 8 into 0.75 plus 2 into z we have calculated 14.94, so x will come out to be 4.485. So 4.485 moles is used and 22.42 moles of oxygen air is used. So dividing throughout by 4.485, so this is the stoichiometric balance, sorry not stoichiometric, the actual combustion process of the fuel. So for 1 mole you are taking 5 moles of air to for the combustion. So this being a rich fuel mixture, so now we need to find out the air fuel ratio. So air fuel ratio is nothing but mass of air divided by mass of fuel. So mass of air is written as number of moles into the molecular weight of air divided by number of moles of fuel into molecular weight of fuel. So here number of moles of air is 5 moles of air we are using. So 5 into 4.76 because 1 oxygen and 3.76 moles of nitrogen. So 1 plus 3.76, 4.76 moles into 5 moles for totally. So 5 into 4.76 and molecular weight of air is 29 divided by 1 mole of fuel, and the molecular weight of fuel is 8 into 1 plus 4 into 12. So we can calculate so it will become 4 into 12 is 48 plus 8 is 56. So 56 is the molecular weight of the fuel. So this will give me 12.325. So this is the actual air fuel ratio for the rich air fuel mixture. So 12.325. So now we have calculated the first one, air fuel ratio. Now the second is equivalence ratio. So equivalence ratio, we need to find out the stoichiometric air fuel ratio to find out equivalence ratio. So we do a stoichiometric reaction. So we take 1 mole of the fuel and some x moles of air, and we say it has totally combusted, so it will be CO2 plus H2O plus nitrogen. Similar approach for balancing nitrogen, oxygen and carbon. We can find out the moles present in the products and the air used. So in the stoichiometric reaction, the balance will be 1 mole of C4H8 fuel. It takes 6 moles of air, so it will combust to form 4 moles of CO2, 4 moles of water, and 6 moles of nitrogen, which is present in the combustion. So for this, the air fuel ratio is same process, 6 mole, 6 into 4.76 for air, oxygen plus nitrogen, 4.76 into 29, 4.76 into 29 divided by 1 into 56. So this will come out to be 14.79. So stoichiometric air fuel ratio is 14.79. So equivalence ratio will come out to be air fuel stoichiometric air fuel ratio divided by air fuel ratio, actual air fuel ratio. So we know stoichiometric is 14.79, actual is 12.325. So equivalence ratio is 1.2. So we know this is a rich mixture, fuel rich mixture. So we have calculated. So now the next question is lower heating value of the fuel. So lower heating value of the fuel is just the way we neglecting the water being after condensation, what is the water remove the amount of latent heat of water if you remove from the high HHV, so that will give me a lower heating value. So to find out the latent heat of water which is vaporized, so for that we assume that for 1 kg kilomole of fuel, so or 1 kilomole of fuel in stoichiometric reaction there is 4 kilomole of water. So for 1 mole of fuel, 4 into 18 into 2 for this is the latent heat 24 HFG 2442.3 kg per kilomole. So we are converting that, 18 is the molecular weight into 4. So this will give me 175.85 megajoule. So this is for 1 mole of fuel. So if we want to find out this in terms of per kg of fuel, so we divide this by the molecular weight of fuel. So 175.85 by 56 will give me 3.1 megajoule per kg, because here QHV is given in terms of we need to find in terms of megajoule per kg, and QHV is given as 46.9 megajoule per kg of fuel. So this is the actual the amount of heat taken for water to evaporate. So we are taking it back, so 175.85 divided by for finding in terms of kg of fuel, we are dividing it by 56, so it will come out to be 3.1 megajoule per kg. So QLHV, as already said, is the heating value divided by minus the heat of vaporization of water. So we have calculated that. So 46.9 minus 3.1, which will come out to be 43.8 megajoule per kg. So we have find out the lower heating value. And next is if the energy released when 1 kg of fuel is burned. So 1 kg of fuel is burned in the engine with a combustion efficiency of 98%. So we know QLHV we have calculated. So QLHV into combustion efficiency into 1 kg of fuel. So 1 into 43.8 into 0.98, so 98%. So we'll get 42.9 megajoule of energy for combusting 1 kg of fuel. So we have calculated all. So the next is moving to the next question. The question is, you have a flexible fuel vehicle operates with a stoichiometric fuel mixture of 1/3 isooctane, 1/3 ethanol, and 1/3 methanol by mass. So there's equal proportion of isooctane, ethanol, and methanol. So you have 3 components, so each is contributing 1/3, and it is operating at stoichiometric fuel mixture. So here we have been asked to calculate air fuel ratio, so motor octane number and research octane number, fuel sensitivity and anti-knock index. So have been calculated, need to calculate all four. So a table is given to find out the octane numbers for corresponding fuels, and that's it. And I can use the molecular weight. So we know the three component isooctane, ethanol and methanol. So isooctane, ethanol and methanol mass, we are assuming all are equal proportion, 1/3. So we are taking one for each because equal ratio. So each of its molecular weight is given, taken from the table, 114, 32, 46. So in terms of moles, how many moles is 1 divided by 114 will give me 0.00877 moles. Because this is by mass, we are converting it to moles. So 32 by 1, 0.03125, and 46 by 1, 0.02174. So this is the number of moles of each component taken. If we are doing by mass, it will be 1 by third. If we are taking by moles, this is the moles, and the total number of moles is 0.06176. So mole fraction will be 0.00877 divided by total number of moles, 0.6176. Similarly for other components, we can find out the mole fraction. So it will come out to be 1. So 0.142, 0.506, 0.352. So now we need to find out the air fuel ratio. So we'll write the combustion equation. So we know the mole fraction of each of the component. So we write 0.142. If we take 1 moles of the total mixture, so that 1 mole will contain 14.2% isooctane, 50.6% methanol and 35.2% ethanol. So that's what is written down in this combustion equation. So 0.142 isooctane, 0.506 methanol, 0.352 ethanol. This along with some amount of air which will be combusting. So that will form stoichiometric. So everything will get converted. So C will convert CO2, H2O plus nitrogen. So doing an component balance, we can find out the moles. So this will come out for 1 mole of the fuel, we'll get 3.59 moles of air which is required. So air fuel ratio is mass of air by mass of fuel. So we are writing in terms of mole numbers and molecular weight. So Na we know for air is 3.59 into 4.76, oxygen plus nitrogen 4.76, 3.59 into 4.76 into 29 mass of air divided by each component and each of its molecular weight. So it will be summation of the mole numbers into molecular weight of each of component. So 0.142 of isooctane into 114 of isooctane plus 0.506 of methanol into 32 plus 0.352 into 46 of ethanol. So this will give me an air fuel ratio of 10.2. So now we have balanced, we have found out the combustion equation, we have found out the air fuel ratio. Next is we have to find out the motor octane number and research octane number, fuel sensitivity and anti-knock index. So from the table for isooctane, we know the motor octane number is 100, research octane number is 100, and then is ethanol and methanol. Methanol is 92 MON and RON is 106. Ethanol is 89 and 107. So we know MON and RON. So we can calculate the total MON and RON of the fuel is nothing but the mass fraction into the octane number. So 1/3 into 100 plus 1/3 into 92 plus 1/3 into 89 of same isooctane, methanol and ethanol. Substituting that, we will get the MON of the fuel is 93.7. So we get 93.7. You see is close to the middle component. So because it's equal proportion, so 93.7. Similarly, RON, we know RON is 100 for isoctane, 106 for methanol, and 107 for ethanol. So similarly, one third, one third, one third proportion. So when I am multiplying by each of the RON, the total RON of the fuel will come out to be 104.3. The fuel sensitivity is the difference between RON and MON, how much it's varying, the sensitivity, octane number is varying. So that is the fuel sensitivity. So in this case, RON minus MON is 104.3 minus 93.7 is coming out to be 10.6. So the fuel sensitivity is 10.6, and anti-knock index. So anti-knock index is MON plus RON divided by 2. So this is the average of the two values. So anti-knock index, it will be 93.7 plus 104.3. So divide by 2 will give me 99. So anti-knock index is 99. So we have found out all air-fuel ratio. We have found out MON, RON, and the fuel sensitivity and anti-knock index. So everything can be found out. Okay. That's it for today. Thank you.